Thank you, Jose Pablo. Thank you, Fernando, for organizing this webinar and for giving Kwabena and myself the opportunity to present. Thank you also to ISGAN and to the European Copper Institute for the organization and the opportunity as well. So welcome everyone to the webinar on the need to model coupled energy networks to transition to a decarbonized future. The webinar will be presented by myself and by Kwabena. We are both the co-founders of encoord. encoord is an energy systems modeling software and consulting company, and we are based in Essen, Germany, and in Denver, Colorado, in the United States. So I would like to start by giving a little bit of background regarding, the need to model coupled energy systems. So right now, what we are seeing around the world for obvious reasons is we have countries, governments, states, for example, here in the United States, companies and private initiatives in general, whose common goal is to find ways to decarbonize the entire economy. And this is going to be a major challenge because of the sources of global anthropogenic greenhouse gas emissions. As you can see from this graph, with information from the IPCC, greenhouse gas emissions come from a wide range of different sectors of our economy that include, transportation, electricity and heat production, different industrial applications, buildings, other energy uses, and also include agriculture, forestry, and other land use. In today's presentation, we are going to focus on 3/4 of global anthropogenic greenhouse gas emissions. So we are not going to discuss agriculture, forestry, and other land use, but we are going to discuss different pathways and different solutions to decarbonize 3/4 of global anthropogenic greenhouse gas emissions. So as you all know, one of the major advancements that we have seen during the past decade or 2 decades regarding the reduction of greenhouse gas emissions in our economy has mostly come from the electricity sector by a further integration of renewable energy sources mostly, and then in the United States, for instance, as well as other parts of the world, the displacement of coal and the increase of natural gas for electricity generation. However, as you can see from this graph, that's less than 1/4 of total global anthropogenic greenhouse gas emissions. So even if we were able to fully decarbonize the power sector, we will still have challenges regarding the other sectors, which we may all argue that a lot of different sectors can be electrified, but we will discuss later how that may not be that simple or not applicable in all cases. So I would like to discuss what I believe are 2 of the major challenges to decarbonize our economy. The first challenge is the need for long-term storage in the electricity system. As I mentioned before, right now, the electricity system can be seen as the central system to decarbonize the economy by integrating renewable energy sources or carbon neutral sources for electricity generation, and then by electrifying as much of the other sectors. However, the challenge of decarbonizing the power sector is that unless you have a system where you have a lot of hydro power potential, if you rely mostly on variable renewable energy sources such as wind and solar, you will always have an imbalance between wind and solar generation and electricity demand from a seasonal perspective. What I say by that, as you can see from this graph, this is a graph from a study that was done in the United States for the state of California that looks at for every month of the year under a 100% renewable energy penetration power system, what will be the the seasonality of solar generation, wind generation, and electricity load. And what we can see here is there is always going to be periods in the year where you generate more electricity than you consume, and there is other times of the year where you generate less than what you consume, or in other words, you consume more than you can generate with your wind and solar power. This graph to me is a clear explanation of why we need long-term storage in the electricity system to be able to fully decarbonize the power system and to do it in a more efficient way, to not have to overbuild enormously the system. Even if you were to overbuild the system enormously, there is many studies that show how you're always going to have periods of the year where you're not going to have enough renewable sources to cover your demands. And these periods may not be very frequent and may not be very long, but long enough to require some relevant amount of long-term storage. As you all know, there has been a lot of discussion lately about the need for, or the value and the need for battery storage in the power system, which I completely agree with. However, batteries are mostly used for short-term storage and for either few hours or maybe up to a couple of days. It is unthinkable to imagine to store energy in batteries, to discharge them a few months later in the year where now we have a need for more resources. So I will get back to that later, but one way of obtaining long-term storage is by coupling different energy systems, and I'll explain later what I mean by that. The second major decarbonization challenge is the need for carbon neutral fuels for processes that cannot be electrified. And here what I mean is what I was mentioning before, is that we can electrify a lot of different sectors. For example, short distance, light road transportation. For example, I live in Colorado, and it's probably one of the states in the United States that has most electric vehicles. Here, I will say that at least a third of the people I know personally, they don't drive any more combustion engine vehicle anymore. They all drive an electric car. So we're already seeing how, for example, transportation can be partially electrified. Heating can be electrified, mostly, for example, using heat pumps, and some industrial processes as well can be electrified. However, as we can see in this graph from a very interesting paper that was published 2 years ago in Science, we can see how there is several sectors of the economy, for example, industrial sectors like iron, steel, and cement, industrial processes where it is very hard to electrify because of the need of combustion. And therefore, you need some sort of fuel to reach very high temperature for certain processes. In other cases, it's due to the flexibility that, for example, you may need in load following electricity generation, or, for example, the need for storing energy in a high density, for example, for aviation, shipping, and other long distance road transport. So in this graph, what I want to say is we cannot fully decarbonize the economy if we focus only on electrifying the economy and on decarbonizing the electricity sector. We must find a source of carbon neutral fuel source. And what I believe is the major potential solution is by integrating and coordinating coupled energy systems, primarily the power network and the gas network. As we all know, these two systems are already interconnected, even if they are not planned and operated in a very coordinated or in a common way, but they are highly connected. For example, in the United States, the electricity system highly depends on the gas network because the major source of electricity generation is gas-fired power plants that are all connected to a gas pipeline network. So what we see from this picture is that gas turbines that burn gas, or demands in the gas network, are major injection points or major generation in the electricity network. However, there is two other types of links between the two systems. One is power to pressure. What I mean by that is there is several gas compressor stations, and those numbers are potentially increasing, that are electric driven, meaning that now the gas system also depends on the electricity system. And then there is the power to gas connection, which is still at the very early stage, mostly developed in Europe at this point, but still majorly at demonstration pilots throughout different countries in Europe. And this is the major point of discussion of this presentation, power to gas. Power to gas is the ability to generate gas by consuming electricity. And I'll discuss later how that is done. But this is giving the opportunity to create a carbon neutral fuel that then can be either injected in the gas network, or it can be used for other purposes that, again, I'll discuss a little bit later. But here I want to discuss about also the link that these two systems have with the heat network. The heat network, I haven't really discussed about it yet, but it is by being able to enhance the integration and the coordination between the electricity system, the gas system, and the heat system that they are connected to, because heat is either generated by electricity mostly, or by gas boilers that burn gas, or by cogeneration plants that burn gas or other fuels to generate electricity and heat. And one of the major values of enhancing the coupling between heat networks mostly with electricity, but also with gas networks, is the potential source of enormous storage that heat networks can provide. As you all know, we are familiar with electricity storage. We already discussed a little bit about it, the difference between short-term and long-term storage. Gas networks, something that is unique compared to power networks, similar to heat networks, is that they store energy in the network. For example, in gas pipelines, you already store an enormous amount of storage. If I'm correct, I don't remember the exact figure, but I remember reading that, for instance, the German pipeline network, in average, at any moment in time, stores within the pipelines about the gas consumed in Germany over 3 days. That cannot be said, for example, about the electricity network, where generation and demand must be equal at any moment in time to maintain the reliability of the system. So heat networks add another source of storage for the overall energy system, which will give additional flexibility to be able to integrate more renewable energy sources. And it is a source of temporal arbitrage that will allow to better manage or more efficiently manage the imbalance between renewable generation, renewable resources, and energy demand in general, that be for electricity purposes or that be for heating, for example. So I want to now move back to power to gas. As I mentioned, power to gas is what I believe one of the major solutions to decarbonize the economy by using electricity, ideally excess or curtailable renewably generated electricity, for example, from solar and wind plants, with the use of water to generate renewable hydrogen gas using power electrolyzers that take advantage of the of electrolysis that can split water into hydrogen and oxygen. Another hydrogen is a renewable gas that can be used for many different purposes. And I'll discuss a little bit more about that. One thing you can do is store it in pipeline systems for later use. In natural gas pipeline system, you'll be limited by how much you can inject. And there is a lot of discussion now in Europe what that limit should be. And people are discussing from a couple of percentage points in volumetric terms up to even 20% in volumetric terms. But I'll discuss a little bit more about that later. Of course, we are all aware about some of the challenges of hydrogen. And what is interesting is now we could also use this hydrogen in another kind of power to gas technology, which is instead of using the hydrogen for the end use, now we can use the hydrogen with captured CO2 from the air or from different industrial processes or any processes. We have plenty of them nowadays that generate carbon dioxide emissions. Use a bioreactor or some other type of methanation reactor to generate methane, which is, in other words, the same molecule as natural gas, CH4. So in a way, you are creating a renewable gas that is very similar to the natural gas that we are extracting today and that we are using in so many different applications for electricity generation, for heating, for cooking, for example, for industrial processes, and for transportation, and so on. So power to gas is giving the opportunity to link the electricity network with the gas network, that be the natural gas network, or that be even a pure hydrogen network that we may envision for the future. So we can take advantage of the imbalance between electricity or electricity generation from wind and solar and electricity demand. And we can use the unused or curtailed electricity generation from wind and solar to generate hydrogen with an electrolyzer. And then that hydrogen, we can either use it as it is, or, as I mentioned before, convert it to renewable methane. In either way, we can use the hydrogen either in a natural gas pipeline network by simply injecting it and blending it with the natural gas and other types of biogases, for example, that we may want to inject in the gas grid. We may use methanation to convert it directly in methane, or we can imagine a hydrogen network or a hydrogen system that delivers hydrogen, for example, for storage. So now you could use all the hydrogen you're generating and store it in very large quantities, and that could represent a way of storing energy for long terms for the power system, and then use that hydrogen, for example, in fuel cells to generate back electricity. You can also use it for directly as a fuel for industrial processes. There is many industrial processes already today that already use hydrogen, but maybe not renewably generated. And then you can also use it for transportation purposes. So hydrogen, the way I see it, and the way many people have been talking about it, and we've been hearing a lot of talks about hydrogen. I think we haven't heard about hydrogen for a while, and then suddenly in the past 2-3 years, hydrogen seems to be coming back as one of the major solutions for the decarbonization of the energy systems. And people are starting to call it the oil of the future. And it is because it has the potential to become a major source of fuel that is carbon neutral, and that can really help decarbonize many sectors of our economy. And it can help also decarbonize the power sector by providing long-term storage. I'm realizing that I may have lost the connection. Can you all see my, can you see the slides?
Yes,
I think
we can see the slides.
Okay. Can you see the one that says modeling challenges now?
now is black.
Okay, sorry, give me a second. I want to make sure you are seeing it. Okay, can you see it now?
Yes.
Okay, I apologize about that. I don't know what happened. Okay, I'll continue. Okay, so I gave a very detailed background about the need to couple different energy networks. And now I switch more to modeling, which is why do we need to model them? So historically, energy systems, for example, electricity networks or natural gas pipeline networks, they have been planned and operated independently. And therefore, different software tools have been used to model different energy systems. The physics of the two systems are different, and they've been planned and operated by different people, different institutions. And therefore, the software that have been used to model them to inform planning and operational decisions have been different. So it is very hard to model the interface between coupled energy systems when you're using different tools to model each of them. And generally, it is also a very time-consuming and error-prone process. Moreover, when modeling different energy systems independently, it is not possible to correctly represent behavior of coupling elements like gas-fired electricity generators, power-to-gas technologies, and, for example, electric-driven compressor station, while considering their impact on the two or more systems they are part of. What I want to say by that is, when you have an element that belongs to two systems, if you are only modeling one of the systems, you cannot really correctly model how the system behaves and how it impacts and is impacted by what is going on in the two systems or three systems it is connected to, in case it is also connected to the heat network. So here is where we talk about what we believe is a solution for this modeling challenge. How do we model two systems that are coupled? Because the coupling is becoming so important, how do we model them when we have different tools? Well, our solution is the Scenario Analysis Interface for Energy Systems, or SAINT, which is a software application that can model, plan, and operate coupled electricity, gas, and heat networks. SAINT is the only commercial software that today can model coupled energy systems using different modeling approaches that include simulation and optimization algorithms, all in a single environment and graphical user interface. What do I mean by that? In the same software, in the same platform, a user can model an electricity network, it can model a gas network, and we are now developing the capability to model a heat network as well. And you can model any of these networks either independently, but you are still using the same framework or on the same software, or you can model them in a coupled way, meaning that you are now, instead of solving a set of equations that describe one system and then iterating with solving the equations that represent another system, you are solving them together with the equations that represent the coupling elements, for example, a gas-fired power plant or a power-to-gas technology. Moreover, we believe that, I imagine many of the people attending this webinar are energy system modelers. And as you all know, modeling a system is trying to represent with a mathematical formulation a certain behavior of a system. And you can model a system for many different reasons. You can model it for planning reasons. You may want to find the optimal investment, for example, in generation and transmission in a power system, or you may want to run it to optimize operations, for example, in an electricity system to commit and dispatch electricity generators. Or you may also just want to run a simulation to understand the steady state or dynamic physical behavior of the system, for example, to study the reliability and the resiliency of the system under different scenarios or under different operational conditions. So what in Saint, what we allow the user to do is to run different modeling approaches for any energy system, and that applies when you're modeling an energy system independently or when you're modeling it in a coupled way. So in other words, you can model an electricity network, for example, using a long-term optimization model or a short-term optimization model if you're doing, for example, capacity expansion, or versus you're looking at the more of a production cost model to minimize cost of operating the system. And then you can run, for example, an AC steady state simulation or a dynamic simulation, similarly to the natural gas network. Now, we are a relatively young company, so we haven't developed all of these yet. Currently, in our commercial version, we have 2 natural gas network modeling approaches or modules, which is steady state and dynamic simulation of natural gas networks. And on the electric network, we have steady state simulation, so AC power flow. And we also have 2 short-term optimization modules, a AC optimal power flow module, and we are currently finalizing the development of a full detailed unit-convenient economic dispatch short-term optimization module. So currently, Saint is used by our clients and our partners to model real large-scale electricity and gas networks. And here I want to mention a couple of characteristics that Saint have that I believe are very relevant and valuable. We're trying to model electricity and gas networks in a coupled way. So Saint can model the injection and blending of different gases, meaning now you can model how a power-to-gas facility that is a demand in the electric network injects a different gas quality in the gas network. And you can track that quality throughout, that gas composition throughout the system. And we will see a little bit more of that later. Saint also allows the user to model coordinated controls between coupled energy systems, meaning now you can apply a control on the electric system that is a function of a variable or of a condition in the gas network and vice versa. I want to mention that Saint has also been validated by benchmarking it against scientific literature and other commercial software, and that Saint is highly interoperable with other tools thanks to its application programming interface, its API. So you can actually connect Saint with other software that may be modeling other networks that Saint doesn't currently model beyond electricity and gas networks at the moment. So why would someone want to use Saint? Well, you may want to use Saint to save capital and operational costs of both electricity and gas networks. You may want to use Saint to take better investment decisions, considering the coupling of electricity and gas networks, looking in future scenarios in assets both in the electricity and gas networks. You may also want to use Saint to reduce the cost of operating both systems. And, you know, related to that, to understand really how do the 2 systems, electricity and gas network, work together, and how can you increase as an operator the efficiency of operating both systems. You may also use it to improve system reliability and security of energy supply in electricity and gas network, for instance, by looking at how a contingency in one system not only affects one of the system, like that system, but how does it affect the other system it's connected to. For example, how does an outage in the electric system affect potentially compressor stations in the gas network, and how the gas network affected. And finally, you can use it to find ways to reduce greenhouse gas emissions overall, for instance, by using curtailable electricity to generate renewable hydrogen and inject it in the gas network. Users of Saint include transmission and distribution network operators of both electricity and gas systems, governments and energy regulators, and also definitely research institutions and universities. So now I would like to stop the presentation for a few minutes and give the floor to my colleague Kwabena, who will show in the software Saint one of its potential application and why it is so important to be able to model two systems, the electricity and gas systems, in a coupled way. Thank you, Kwabena.
Thank you very much, Carlo. Hello, everybody. My name is Kwabena Pamburo, and I'm going to show you a short demonstration of Saint. Can you please confirm if you can see my screen? Maybe one person in the panel?
Yes, we can.
Okay, perfect. Yeah. Thank you. All right, so here you see on the current screen, you see the graphical user interface of Saint. As Carlo has mentioned, Saint is a software tool that can be used to model and simulate coupled energy networks, which in the current version includes a gas network and electricity network. In this demonstration, we are going to model the gas and electricity transmission network of Belgium, which is, this one is a simplified model of these networks. And I have already loaded the network model into Saint. You can see in the left map window, you can see the gas transmission network of Belgium, or a simplified model of the gas transmission network. On the left, and on the right, you can see the electricity transmission network of Belgium. So now we want to actually couple these two networks, so the gas network and electricity networks, at specific coupling points. And then we want to run a simulation, basically a transient gas network simulation and a quasi-steady state AC power flow simulation, where we consider also the coupling elements between them. In order to show you how these two networks are coupled, I'm going to visualize the two networks in one map. So I'm going to close the right map, and then I'm going to, let me just close this. I'm going to visualize both networks in one map. And if I do so, you will see here the gas and electricity network both in this map. And I'm going to zoom in into some of the coupling areas to explain a bit to you what coupling or what links were defined for this example. So the cyan dash dotted lines represent the coupling points between the electricity and the gas network. So here is a coupling between a gas turbine and a gas station, which means the gas turbine that is connected to the electricity grid extracts gas from the gas pipeline in order to burn the gas and then produce electricity and inject it into the electric grid. Another coupling that can be defined is the coupling at electric-driven gas compressor stations, which is shown here in this example. So here is a gas compressor station. A gas compressor station is needed to increase the pressure of the gas for further transportation. But of course, in order to increase the pressure of the gas, we need some energy or some power to do this process. And this power can either be from a gas turbine that is at a gas compressor station, or it can be from an electric motor. And this electric motor will need electric power from the electric grid in order to drive the compressor. So in this example, we defined an extraction of electricity from this bus in order to power the electric engines in the gas compressor station that is located here. So this is this connection. And then last, the coupling that I want to focus on in the remainder of my demonstration is the coupling at power to gas facility. So in this example, you see here within this is the gas network. We have here a power to gas facility, and this power to gas facility should extract electricity from the electric grid in order to produce hydrogen and inject the produced hydrogen within the electrolyzer and inject the hydrogen into the gas grid. So this hydrogen injection, somehow it needs to be modeled at this point. And the way we model the hydrogen injection is, I'm going to show you very quick a window where it is shown. So basically we define a gas quality for this node. And within this gas quality definition, we can basically define what is the, one second, what is the mole fraction, just 1 second, what is the mole fraction that we want to inject at this node. And as you can see here in this property editor, we can define different typical chemical components of natural gas, which includes also here the hydrogen as one of the components. And in this case, we defined 100% hydrogen. So we are gonna inject 100% hydrogen at the node where this power to gas facility is located. But obviously we could also change, we could also define a different mole fraction that we inject here. For instance, if we had a reaction, a methanation process at this power to gas facility, we could also define the mole fractions accordingly by, for instance, adding some fraction of methane to this, to this distribution, to this fraction distribution. So now, we have defined the hydrogen fraction at this node. So this is the hydrogen is going to be injected at this node. But as you probably will admit or will see, when we inject hydrogen at this node, we will have a blending between the gas, so the normal high calorific natural gas that is coming from the upstream pipeline, with the hydrogen that we inject at this node. So we will have a blending of these gas, and as you know, hydrogen has a lower calorific value per standard cubic meter than high calorific natural gas. So we are going to change the calorific value of the gas that goes downstream. Then downstream, so downstream this point here, we have also other customers that are connected to the gas grid. For instance, there is a customer here, which is again a gas turbine that will extract gas from this gas station in order to produce electricity. So you can imagine if we inject here hydrogen, this hydrogen will move with the velocity of the gas stream, which is probably around 8 meters per second, 10 meters per second. And as the gas stream moves, it will change the quality also at this node. So meaning the calorific value of the gas at this node is going to change if we inject more hydrogen. But if the calorific value changes here at this point, it will also mean that the amount of gas that we need to produce a specific amount of power in the electric grid will be higher compared to the case where we did not inject hydrogen and had only high calorific natural gas passing through the pipeline. So you see here we have a coupling between the two networks with this, which is a bidirectional coupling. And if you want to model this kind of problem in the traditional tools where the systems are modeled separately, you would have to do a kind of an iterative process, but you will fail because you cannot reflect the actual bidirectional coupling. So that's where we step in as encoord, and also using Saint. We model these interconnections between the different energy networks, between the gas and electricity network, in one simulation time frame, so in one matrix, where we reflect the physical equations for the gas network, the physical equation for the electricity network, and we define the coupling equations that describe the interlink between the two networks. We describe all of them in one matrix, and we solve the entire problem for each time step so that we can directly reflect the interdependency between these two networks in each simulation time step. Okay, so I'm going to run very quick the simulation. So this is basically a 24-hour simulation with a time step of 15 minutes. We are running a transient simulation on the gas side and an AC, a multi-time step AC power flow on the electricity. I'm just gonna execute the simulation. Give me just a second. I go on simulation and I click on combined simulation. So now it is running this simulation in a coupled way. And as you can see, we get also some log output which tells us what is currently happening in the simulation. The simulation also considers the constraints that are in the systems because, for instance, you may have a pressure limit at some of the nodes within your gas network. And there will be some times where maybe you go below the pressure, then the system will adapt the controls of different facilities in the gas network in a way that all the solutions, so in every time step, you have a solution that is within the operating region. So the simulation has finished. And now we're going to have a look at some of the results, and we will focus mainly on this part with the power to gas facility. To open some of the results, I'm going to, just a second, I need to move this icon. So I go on view and I click on chart, and now we can have a look at some of the results. Just put this in and zoom in. So let's have a look at the results for the power to gas facility. If I click on the power to gas facility, then what do we see here? We see in this right chart window, there is a plot on the center right, which tells you here it's the Q, which is in 1,000 standard cubic meter per hour, and it's basically the injection of hydrogen over time at this node. So as you can see, there are times where we inject hydrogen into the network, and there are times where we do not. And these are basically the times where we have excess generation from the electric grid, okay? So when we inject hydrogen to the network, obviously this is gonna change the mole fraction of the blended gas at this node. And this is shown in the left center plot, where you see the mole fraction of the different, of some selected gas components. XC1 is methane, XC2 is ethane, then CO2, then nitrogen, and then hydrogen is XH2. And as you can see, as we inject hydrogen into the network at these times, so between where we have these peaks, you see that we have also some peaks for the hydrogen. So the green line has also these peaks. So as we inject hydrogen, we reduce the mole fraction of methane, right? And this in turn has an effect on the calorific value. As I mentioned before, the calorific value of hydrogen per cubic meter, per standard cubic meter is lower than the calorific value of high calorific natural gas. And as we inject hydrogen, we are reducing the calorific value of the blended gas, which is shown in the top left plot, where the blue line shows the calorific value over time, and the green line shows the Wobbe number over time, okay? So now when we inject hydrogen, as I said, this blended gas at this point will travel downstream, and it will affect also the customers downstream that extract gas from the network. So let's have a look at one of the gas customers here, which is this gas station. If I click on this gas station, you will see that this hydrogen injection, it moves slightly in time because of the time needed to transport the gas from this point to this point, because I have a pipeline here. So the gas will need some time to move from here to here. So now you see that the calorific value reduces, and this is mainly because we inject hydrogen at this point. And if this calorific value reduces, then if I need the amount of gas that I would need to produce electricity will be larger than if I only had a high calorific methane injected at this point. And this in turn will have an effect on my pressures in my network, because if I inject, the more gas I extract from this point, the lower the pressure gets, because I am removing line pack from my pipeline, and this will reduce also my pressures. So you see that these two networks, they are highly interconnected. And in order to really find out these kind of interdependencies between these networks in such a bidirectionally coupled system, the only way to do it is to solve these systems in a coupled way, considering the physical equations and the coupling equations between them. So because of lack of time, I will stop here. And if there are any other questions during the Q&A sessions, I am available to answer them. Thank you very much. And I give the mic back to Carlo.
Thank you, Kwabena. So I will now try to wrap up the presentation. I know we went a little bit over the time we had planned. I apologize for that. And I would like to end by showing you very quickly 3 case studies in which SAINT is used for modeling coupled electricity and natural gas networks, and how, you know, there is different type of institutions that are interested in the coupling, in the ability to model coupled gas and electricity networks for different reasons. The first one is the European Commission's Joint Research Center is using SAINT to model coupled European electricity and natural gas networks to run analysis of security of supply in integrated gas and electricity networks. And they are running feasibility and contingency analysis, as well as developing and testing mitigation strategies. As an example, one of the type of contingency analysis that one could do is if there is a contingency in one of the gas supplies. Let's imagine a situation where one of the countries delivering gas to one of the European Union countries has an issue and cannot continue the delivery with the gas. How does that affect the gas network overall in Europe, and how does that then affect the electricity network? And vice versa, one could imagine a situation in where an outage in the electricity network may affect the gas network. By running this coupled simulation, you can understand the interdependencies between the two systems and the impact of an outage in one system on the other one. As a different example, the National Renewable Energy Laboratory in the United States is using SAINT to look at scenarios of high wind and solar penetrations. As we all know, what we are seeing in high wind and solar penetrations in the United States is we see an increase in the variability and uncertainty of operations of natural gas generators. So the goal of the study where they're using SAINT for is to analyze the value of coordinating electricity and natural gas network operations in the day-ahead and intraday timeframes, mainly looking at scenarios with high wind and solar penetrations where the large variability and uncertainty that wind and solar bring to the system affect the way gas plants are operated, and therefore by modeling the coupled modeling the two systems in a coupled way, they are able to see and value the impact of a higher coordination between the two. And in this project, they collaborated with, for example, Kinder Morgan, which is a major natural gas transmission network operator in the United States, and to validate SAINT's natural gas simulation modules, but also to simulate Colorado's interconnected electricity and natural gas network under high renewable penetration scenarios, and understand what is the value of coordinating the operations of the two systems. And what they found is that most of the value comes from reducing cost of operating the two systems and reducing the chances of not being able to deliver gas to the gas-fired power plants, and therefore the potential impact on the ability of the system, of the electricity system, to meet its demand needs. And then finally, TenneT, which is the electricity transmission network operator of the Netherlands and the west of Germany, is using SAINT to model or to run coupled simulation and analysis of gas and electricity networks, and mostly interested to look at optimal sizing and location of power to gas facilities, for example, power to hydrogen facilities that consume curtailed electricity in the power system and inject hydrogen in the gas system, and also running contingency and security of supply analysis. So they're using it for their future planning studies. And this coupled modeling capability gives them the opportunity to include the connection of their electricity transmission network how it's coupled in the future with a gas network or even potentially a new hydrogen network. So the major key messages I would like to share at the end of this presentation is that one of the major challenges, as I mentioned, to decarbonize the electric sector is the need for long-term storage due to the seasonal variability of renewables and of electricity demand. The hydrogen has the potential to become a major source of energy storage that can be produced anywhere where there is excess electricity generation from renewables via electrolysis, and that the integration and coordination of coupled energy networks such as electricity, gas, and heat networks represent major opportunities to decarbonize a large share of the sectors responsible for today's anthropogenic greenhouse gas emissions, including electricity and heat production, but also buildings, transportation, and different industrial processes. And finally, that the best way to study and understand the coupling and the synergies of different energy networks is to model them in a coupled way. And I like to end by saying that we believe that the integration of energy systems and the coordination of their planning and operational processes are needed to achieve the challenging economy-wide decarbonization goals. And we thank you very much for your attention, and we would like to welcome any of your questions. I apologize for taking longer than we expected. We will stay around for a few more minutes to be able to answer all your questions, but if you have any other questions or you're interested in knowing more, please email us or visit our website. And by the way, the webinar will be has been recorded and will be available at the link I have provided here in the slide.